This stage is yours.
All right, there we go. All right. Hello, everybody. I'm aware that I'm the last speaker, and I'm standing between you and the cocktail, so I'll try to keep it brief. Just a little bit about myself, so you get an idea where I'm coming from and what my own lens is. So I'm trained as a particle physicist, coming from a kind of theory-driven background. So I worked at CERN for many years. And then for the last few years, I've been working at a couple of software companies, most recently a company called Arundo, which builds data-driven solutions for engineers. In this case, engineers like people who stand on rigs with hard hats and wrenches and that kind of thing. And now I work at a company called Graphcore. It's a British company, and they make computer chips, a little bit like GPUs or TPUs, which are optimized for deep learning. A little bit of a plug, we're hiring currently in Oslo, so if anyone's interested in going into deep learning focused hardware, let me know. And I'm going to talk about how to build data-driven solutions for engineers that stick. And by stick, I mean that they actually use, which would imply solutions that make it into production. So from prototype to production. I'm going to give away the punchline already because I already did in the panel. To me, the best way to do that is not to think about these two things as two separate stages, but rather how do you set up a system which is already production ready from day one, so that it's actually driving decisions in an organization and therefore making or saving money or improving safety or doing something that's worthwhile. All right, so just a couple of definitions before I kick off. So what is a data-driven solution? What do I actually mean by that? Everyone's got their own definition, and I thought I'd just throw mine on the board as well to add it to the mix. So from my view, there's two different ways of doing advanced analytics. There's number one, you can start from the system you're trying to model. And that's what I did in my previous life as an academic. So when I was working at CERN, this chart you see on the top left is the Higgs boson discovery. So in 1960 something, Peter Higgs sat down and he wrote down the equations of the universe. It's kind of crazy that you can do that, but you can. And he said, okay, well, to kind of fix these equations, we need some sort of mechanism that accounts for mass. We know that particles have mass, we observe it. In the 1960s, there was no term in the equation that generated mass for particles, so something's amiss. And he said, if you build a detector to look at particles at this energy regime, you should see a little bump in the chart. So he said that in 1960, and then 40 years later, a bunch of people, including me, a lot of people, went and built these experiments to look for these anomalies. And as you can see this bump, and that then you can claim discovery of this particle. So the reason why I'm going on about that is you're starting from the underlying system, and you're building, you're making observations and data which will confirm or deny your hypothesis about the system. And so I would call that a theory-driven approach. And then on the other side of the spectrum, you've got people like Amazon, who are going for what I would call a purely data-driven approach, where they're absolutely drowning in data. Google, Facebook, all those guys who are lucky enough to have loads of it, build build models on that data that make some sort of inference about the underlying system. The thing is that Amazon doesn't give a monkeys about the underlying equations that make people buy the books they do. They just care about predictability. So they can go for fairly black box type of models that will make the right predictions. Also, nothing goes disastrously wrong if they get the wrong answer most of the time, unlike, say, engineers on rigs, where you have to really understand what you're doing. So when I talk about data-driven solutions in this talk, I'm either talking about the ones on the right or something in the middle. So just to kind of by the by, I've started seeing quite a lot of things coming out recently about physics-informed data science, theory-informed data science, which is oftentimes using neural nets where you kind of put physics equations in the middle of them. So it's a really interesting kind of hybrid approach. There's lots of other hybrid approaches where you're kind of leaning on the data science, but also embedding the thing in an underlying system as well. So I'm talking about something towards the right side of the graph, which has its own unique challenges, one of which is, one of the main ones, as I said earlier, is this issue of you don't know always whether your model's going to work until you've built it. It's not like building a purely software-driven product where you kind of know it's going to work. It's just a case of dividing up the tasks and building them one by one. When you're doing machine learning in particular, you've got the data set. Is there any predictability in the data set? Does your data set describe the phenomenon that you're ultimately trying to model? You don't really know until you've built it. And so if you're trying to build a productionized solution, then that causes some problems, as we were discussing in the panel. All right, but you want to do it, because under certain conditions, data-driven solutions have advantages over purely engineering-based solutions. Often, so I did a stint working in Formula One racing. So to give you an example, if you take a Formula One analytics team, they often have lots of people with PhDs in stuff like computational fluid dynamics, so they're taking this theory-driven approach, and that works very well for a car that's in a vacuum. However, if you've got a car which is in traffic conditions, you get all sorts of like non-linearities in the temperature gradients and the airflow and whatnot. And so your equations can break down, and your theory-driven modeling approach may not work anymore. And so you might want to start then going into kind of the ML or ML regime to try and improve the model in those kind of situations. So it is something that people want to do. I think this is, from what I've heard, this has really been well-trodden territory, so I'll probably skip over this one. Okay, so people want to take data-driven approaches for certain types of use cases. We're also now in a situation we have a lot of data often because data storage, data compute is increased a lot in complexity. It's increased in capacity, and it's also reduced in cost. So it's a lot easier now to get hold of the data and analyze it. My dad is about 80 now, and he loves to tell me how he was doing machine learning in the 1960s, and so we're not doing anything new. And he was doing it before I was even born, and that is true. You know, they were doing neural nets before probably all of us were born, but the difference is that they didn't have the data, so it's hard to make these kind of models work, whereas now we do, so it's much easier. And a lot of people, I remember this article coming out, I think it really changed the landscape. A lot more people, myself included, decided at this point they wanted to be a data scientist as opposed to what they were doing previously. And so there's a lot of people who have the right kind of skills that you need to do these kind of projects. And many companies want to do it. This is a very commonly used slide. Data is the new oil, I think it was called. Many companies have seen how wildly successful a lot of these American companies have been in using data, and they want to do the same thing. And so what they typically do, they go and hire a lot of data science-y type people, a lot of machine learning engineers. They get a data lake, and off they go. Now, the problem is, having worked as a consultant with many companies, how to make the most of your data kind of endeavors, I'm sure like a lot of other people in this room, I've seen many efforts, I've done personally many efforts, which have ended up in the dreaded PowerPoint graveyard. I love PowerPoint, it's a great tool, love Microsoft, not knocking them, but it's not where you want your data science models to end up. I think we probably all agree on that. So if you end up in PowerPoint land, as a consultant at least, you hand over your PowerPoint saying, these are the results, and go away and then come back in 6 months. So how's the model? How's it all going? I handed you this Python code, and the company will say, well, the person you handed it to, they've left the company and no one else knows how to run that Python code, so we haven't really done anything with it. And it's kind of depressing. It was been personally depressing for me on many occasions. I was a little bit cheered up when I saw this quote, that it's not just me and that my models are rubbish. It's definitely a thing. And you just need to Google data science failure to find out lots of reasons why, lots of examples where this data science approach isn't working. So this is an autopsy of my typical failure that I would see. So I would say one of the most common mistakes that enterprises or companies make is to separate out prototype process from the production one. So just to explain a little bit what I mean by this, like I said, if a company, company X says, okay, we want to make money from data, we want to be more like Facebook. First, they go and build a data lake. It's very expensive and it's very costly. Then they go and hire lots of people with PhDs in things like computer science and machine learning, also very expensive people. And then they say, off you go. Go and do your thing, go and do your models. And what happens is this expensive data science team typically doesn't have people who are capable of writing production-ready code from end to end. They can write in Python, they can write decent Python, but not usually all the kind of plumbing that goes with that. So they go into Python, they get their Jupyter notebooks, and when I say they, I'm also including me, just so that's where data scientist skill sets usually lies. And they also, they've often come straight out of PhD where they've been, looking at the latest and greatest deep learning models. So that's what they do. People also want to keep their CVs, fresh and current, so they want to try really cutting edge stuff. Academics are a curious bunch by their very nature. And so they'll go and build some fairly complex models. And that is what ends up in the PowerPoint graveyard very often. At the same time, you've got the business on the left hand of that side. So the business is what is driving the product or perhaps project requirements. Business is often talking to the engineering organization a lot more than they're talking to the data science organization, because the data science organization is much newer. Software engineering, has been around for a long time. They have, in my opinion, way more mature processes for doing these kind of things than data science usually does. And so they're kind of coming top down, and data science is going bottom up, when top is business and the bottom is data lake, and you kind of miss each other in midair. So you end up with two kind of siloed parts of the organization, and you're not really centering things around a product that actually changes or influences decisions. So that's kind of fairly typical from what I've seen with data science endeavors that don't go so well. It's very common. Again, another fairly depressing Gartner quote. These are getting a bit old, actually. I should update these numbers. I think I've had these for a year, but still, I would say that one on the top right certainly resonates with me. So I'm going to now cheer up and stop being depressing and say, so how do you approach initiatives to optimize the chance of success? And to me, that roughly translates as, how do you make sure that your models actually make it into production? Number one, I said this in the panel, I'm going to say it again. Start with a set of questions and not with the data. I mentioned in the panel this plot. I find it a fairly simple one, but an extremely effective one, is to look at both business value and feasibility of different data science endeavors which answer a question. So if anyone's kind of in a position where in your organization, what should we do in our data science team? Start with which questions do you think you can answer, or to put it another way, which decisions do you think you can influence? I find it sometimes a bit easier to think about it in terms of decisions. If you don't change someone's mind somewhere using data science, then you're probably not generating value, because the company that you work for will carry on doing what it's always been doing. So if you start thinking about those decisions, what do those decisions, if you change them, what is the financial value? Like something you can measure in dollar signs of changing that decision. How often do you think you will change that decision, and how much money is that going to make you? So you can actually be quantitative on that y-axis. And then in terms of feasibility, it's a little bit fluffier, but thinking about it in terms of what data do we have that would support that model? Where is that data? Can we get hold of it? What's our estimation the model will actually be successful? And then prioritizing them. I mentioned this Hilary Mason article in the panel, really good one. I would recommend reading it, in Harvard Business Review, where she said, so you end up with a lot of questions on this chart. And instead of just saying, okay, well, we'll pick the one that's closest to the green area, instead trying to draw lines between them. So if you say, we can answer this question, this is the decision we're going to influence, and here's another slightly different endeavor. If we can answer that question, that will enable us to unlock, these other levels, and trying to draw these lines, draw lines between your different points, and then you're basically creating some sort of roadmap. So she explained it way better than I ever will, but so I recommend taking a look at the article. I should have put a link, sorry. Right, next, ensure, and this is more an IT thing, ensure a framework to continuously connect the models to the necessary data points, ponds, and live streams. I mentioned earlier my suspicion about data lakes. So I like to think more about data ponds, getting the data that you actually need to answer the question that you're thinking about at that point in time, and accessing that, gradually building up the number of ponds you've got. This is an IT, more in the IT domain, and joining together ultimately. And then also, really important, influencing decisions usually requires data streams. That's, in my experience, harder plumbing than databases. Data scientists usually know how to work with databases, less so live data streams. So making sure you've got all the necessary software architecture plumbing that you need to be able to do that. And organizationally, so some thought on organization. I kind of covered this a little bit in the panel, so I'll try not to take too long, but I really can't emphasize enough my belief that embedding data scientists into teams centered around products or projects is the best way to do it. By that, I don't mean get rid of a data science organization. I still think it's important to have an organization which reports to, chief data scientist, preferably kind of one with a quite big mix of skills between ML engineering, statistics, and business acumen. And that's for the purpose of knowledge transfer, so having line reporting still up to the chief data scientist, but day by day, your data scientists sit in embedded teams around products. Who is in those teams is dependent on what you're actually trying to do, but in my experience, it's typically 2 software engineers, commercial lead, project manager, and data scientist, and UX UI, which I think is really important. All right, and then step 3 of how to ensure that things go into production is aim to continuously deliver AI solutions of increasing complexity. So I'm quite a big fan of continuous integration. And by that, I mean continuous integration also including your AI model. So to me, having an AI model that gives the right answer is not as important as having any model which is actually embedded into what you're trying to build. So let's say you're trying to build an application, going to stick with the sort of things I usually have been working in. So say a predictive maintenance application that's monitoring the state of health of a piece of equipment and is being looked at by an engineer on a rig. Having that model in that application, even if it's not the kind of application which is in front of your engineer on the rig, having it in an application which works, you can access it, all the plumbing is set up correctly. Even if that model is just saying 5, I think getting to that point first and then actually improving your model predictions is the right way to do it. And what your model should actually predict, what it should do, I think you refer to that roadmap I described earlier with this business value versus feasibility chart of what that model should actually be saying. And so by that, I mean a robust API in software terms. So if you're coding in Python, which is what most people seem to be doing nowadays, making sure you're using something like Flask to actually get that and integrate it with the rest of the front end and the data streams and what have you. And then, once that is set up, which it should be more straightforward than normal, because of course we're all working in cross-disciplinary teams, then starting to increase the accuracy of the predictions. And that roughly translates to increasing the complexity of the model only to the level that you actually need to. So my opinion is it's a mistake to go for a more complex model than you actually need. If a linear regression will do it, go with the linear regression because it's interpretable, and if it's not giving the right predictions, then you know why. So just to go for a predictive maintenance example, because that's what I know best, starting with just threshold alerts. Does your sensors go outside of the range of what you would expect? Once you've done that, you can go to KPIs. So let's try and monitor the efficiency of this compressor or whatever it is you're trying to model. Show that to the engineer, and they'll do the rest. And then anomaly detection. At Arundo, we were doing this using clustering. So you're still kind of k-means. You're not doing anything super fancy yet, but it can be extremely powerful if it's presented to the user in the right way. And this is why I keep on talking about UI, UX. In my experience, they're the best people to help you figure out what is the right way to present certain information to your end user. And then you can start going more complex. So then you go to failure detection, failure forecasting, and that's a sort of regime where you might start looking at some of the more complex models that are on the market. So that's it. To stick, your AI models need to be, number one, ensure that they're an answer to a specific business need or question, and make sure you really, really, really understand what that is. And I do mean at a super specific level, like saying it's going to tell us where we should build our new outlet for our retail. Probably not specific enough. I mean, really down to the UX, UI level, like what exactly is it you're aiming to build? Number two, continuously deployed into working applications. So that's kind of a combination of the IT domain to make sure that the plumbing and infrastructure is set up correctly. And secondly, it's also something that you would get to from cross-disciplinary team. If your data scientist is sitting next to a software engineer, they're going to find it a lot easier to deploy their Python model into a working application than they would otherwise. And then thirdly, explainable. I don't know if you've seen, there's a lot of stuff about explainable AI coming out from Google in the last few weeks. I think that's very cool stuff. Again, worth a read if you haven't seen it already. And also as simple as possible given what you're trying to do. And that's all I had to share with you today. So thanks very much, and see you later at the cocktail.